Hey guys, Mrs. Animal here, and today I'm going to be teaching you about a method for integration called U-Substitution. U-Substitution is the integration counterpart for chain rule for derivatives, and the idea behind it is that you take a complicated looking integrand and you make it much simpler by making a substitution in for one or more of the pieces. If we look at the first example, we have the integral of the quantity x plus 2 times the square root of x squared plus 4x dx. Now on first glance we might be looking at pieces and they might be coming together, and we can look at x squared plus 4 and say, well, its derivative is 2x plus 4, and that's kind of written over here with a scalar of 2. But we need to find out a way that we can make a substitution in to make sure and be concretely positive that that happened. So let's look here and let's try to figure out what the inner function is. The inner function that would require chain rule is going to be the piece x squared plus 4x. It's inside the square root. So let's make our u equal to x squared plus 4x. So right away we can rewrite as the quantity of x plus 2 times the square root of u dx. But the problem is that we have our differential in terms of x and we need it in terms of u now. So what we're going to do is we're going to take the derivative of our u with respect to x, and we get here du divided by dx is equal to 2x plus 4. Now, when we go ahead to make our substitution, we have to remember that everything we want to try to either cancel out or substitute in for. So our differential dx definitely needs a substitution. So I'm going to take over here where I had my du over dx, and I'm going to solve for dx. So I multiply each side by the dx, and then I'll solve for dx by dividing. So I get du divided by 2 times x plus 2. I factored out the common term. And now I'll go over to here, and then I have du over 2 times x plus 2, which went in for my dx piece. Now what you can see happening here is a manipulation of the different pieces. I can bring my scalar out to the front, and I have x plus 2 times the square root of u times 1 over x plus 2 times du. So I see here that I have my 2x plus 2 terms canceling out, and I'm left with 1/2 times the integral of root u du. And now we made a complex integrand into a much simpler integral so that we could evaluate. So I'm going to make this 1/2 the integral of u to the 1/2 du. And I'll use power rule. I'm going to add 1 to the power so it becomes 3/2 and divide by that power. Dividing by 3/2 is equivalent to multiplying by 2/3. I'm going to go ahead and do that. And I add my constant of integration. So I end up with 1/3 times the quantity to the 3/2 power plus c. Now I want to make my substitution, so u, which was equal to x squared plus 4x, I'm going to replace. So I just completed this integral using the U-substitution method, which again is the integration counterpart to chain rule for derivatives. Now let's try another example just to make sure we have it. So the first thing we're going to want to do is we want to identify which piece is the inside function. So in this example we have the integral of sine cubed of x cosine x dx. Now remember, we can rewrite this one as the quantity of sine x to the 3rd power times cosine x dx. If we were to take the derivative, I would definitely want to go ahead and put that 3 on the outside because that is going to be what guides and starts our derivative. So now what's the inside function here? Well, sine x is placed within the cubic function, so u is going to be equal to sine x. When I go and think about making my substitutions, I know that u is going to go in for our sine x, so that's taken care of. Cosine x, which is the derivative of sine x, so if I derive sine x, I get cosine x, and that's going to be important. We'll see why in a second. That hopefully will be taken care of with my dx substitution. So I hope when I go through and substitute for dx, a couple things are happening. Dx now becomes du, and the cosine of x will cancel out. So let's take the derivative with respect to x. I get du over dx is equal to cosine x. The derivative of sine is cosine. And again, I want to solve for the differential dx. So I'm going to multiply each side by dx, and then I'll divide through by cosine. Now some methods, and especially our textbook, what they'll do is they'll keep the du piece, and that's what they solve for, and then they balance out everything else. I think that's a little bit more complicated to do. I don't think for me it's as intuitive as this method, so I like this one, but feel free to look in the book just to see if that's a method that you think you know, works a little bit better for you. So our dx substitution is going to be du over the cosine of x. And again, just like in our example before where the x plus 2 and the x plus 2 canceled out, our cosine of x and our cosine of x are going to be canceling out. So I'm left with the integral of u cubed du. Add 1 to the power, and then divide by that new power, and don't forget your constant of integration. We're going to revert back to our term of x, so we have sine of x to the 4th power, or sine 4 of x plus c. The great thing about these problems are that we have a way to check them, and that way is by taking the derivative. If we go back and take the derivative, which I'll do over on the side here, we have 1/4 sine to the 4th power of x plus c. And if I take the derivative with respect to x, we know we're going to need the chain rule. So I bring down the power to the front, I drop by a power of 1, and then I take the derivative of the inside function, which is cosine of x. The derivative of a constant is 0, so I don't even need to write it. So I'm left with sine cubed of x, cosine of x, and that was our original integrand, so we know we did this problem correctly. So just kind of to reiterate a couple important points about U substitution. When you pick your U is normally chosen to be the inside function, or it's chosen that it's a piece that has its derivative somewhere else in the integrand. So in this example, cosine of x was the derivative of sine, so it was a good choice. In example number 1, we picked u to be x squared plus 4x, and its derivative was 2x plus 4, which is hidden over here in x plus 2. We just have that extra factor. So U substitution is a helpful method, and I hope that this video helped you guys a little bit. And there is going to be a second video because all we covered right now was indefinite integration, and we're definitely going to want to look at a definite integral.